equals to nRT. P is the pressure, V is the volume, N is the number of moles, R is the gas constant. Now you don't have to memorize the value of the gas constant. Well, but if you finish your homework and you've done repeated exercise with this number there, when you finish, by the time you finish your homework, you probably already have that number in your mind already. Now this whole thing, the big chunk after this number, that's the unit for this number. Okay, we don't need you to find this number, although through a particular through a design experiment there, and given specific volume and the pressure, and we can actually determine that experimentally. However, this is a constant that should be given to you when we ask you to use this equation to do calculations. Okay. Now, this is something from your textbook there, and basically give you an insight of what's the relationship between each of the individual gas law that we talked about: Boyle's law, Charles' law, and Gay-Lussac's law. Well, Gay-Lussac's law is not here, and Avogadro's law. So they all are derived from that PV equals nRT. So under this particular equation, from this particular equation, for the Boyle's law, we hold N and T constant. So P1, P times V equals to P times V. So pressure times volume is a constant. Okay, so that's the Boyle's law. In Charles' law, the volume and temperature relationship there, we hold the number of moles and the pressure constant. And for the Avogadro's law there, we hold the pressure and the temperature constant there. And so you can see the relationship between two variables. If you hold the other, and there are four variables in that equation there, R is a given constant, it's not a variable. Okay, so among those four different variables there, and if you hold two constant, the relationship between the other two would be the individual gas law. So you really don't need to memorize any of the equations for the individual gas law. As long as you know PV equals nRT, using that overall equation, you should be able to solve any gas law problems there. So this is something that you will encounter in terms of doing the calculation there. And first thing first, when we introduce that PV equals nRT, the ideal gas law equation there, you always need to come, if you are ever using that equation, or for that matter, if you're solving gas law problems there, if temperature is ever involved, temperature has to be in Kelvin, no exception. Okay? And in each of those individual gas laws, as long as the temperature is not involved, then you can leave the pressure and volume in milliliters and millimeter mercury, that's okay. But whenever the temperature is involved, temperature has to be in Kelvin. And there's no exception there. Okay? And also, you always convert grams to moles if you need to. And say if we give you 25 grams of oxygen gas, well, we need to convert it into moles. PV equals nRT. Mass is not a direct part of that equation there. Mass is related to the molar mass and the volume. Now, if you have the mass and volume in that equation, one of the things that we have here is that one of the quantity that we introduced early on the semester, mass over volume, is density. So density of the gas is involved in this particular, thank you, $5 there, okay? And the density is going to be an issue here. So we could actually use PV equals nRT to calculate the density of the gas. Okay? And in your lab menu, you may have read the description there. We are trying to find molar mass through the study of the density and finding the density of the gas there. Well, we didn't really calculate the density yesterday, but yesterday we do have the volume, we do have a mass measure, so mass over volume will give you the density, and there's a relationship between the molar mass and the density there. So make sure everything that you use, whenever you use that PV equals nRT equation, make sure every quantity that you have before you plug them into the equation there, and they have the volume is in liters, and pressure is in ATM, and temperatures in Kelvin. Okay, these are the different types of calculations, and you will be able to encounter. And we will give you some very specific examples there. So the first example, since we are chem is trying, and the syringe has a volume of 10 milliliter at 1 ATM. 10 milliliter means you have 10 milliliter of air trapped inside there. Okay, and the regular pressure or normal pressure will be 1 ATM. Now, if you block the tip of the syringe and the air cannot escape, then if you want to compress the volume down to 2 milliliter, assuming you don't change the temperature, and you can do this at room temperature, and you have a syringe there, and you plot the tip, and you push the volume down to 2 milliliter from 10 milliliter there. What is going to be the pressure of that air still trapped inside the syringe there? So whenever you are asking, whenever you're asked to do gas law questions there, we would prefer that you set up a data table there and try to figure out what is given, what is being asked. And from there, in the calculation, well, you can clearly see, once you have the data table there, you will be able to determine which gas law you're going to be using. And all in all, if in the end, if you decide to plug everything into that PV equals nRT, well, you can clearly see, in this case, temperature is constant, so temperature will cancel out. Okay, so number of moles, the amount of gas is also constant. We have the air trapped inside the syringe, so the total quantity is not changing. So in this case, and we're going to use Boyle's law, PV equal to PV, and you should be able to make a prediction there. 10 milliliter, 1 APM. The volume goes from 10 milliliter all the way down to 5 milliliter, to 2 milliliter, so it went down by 5-fold. The pressure has to increase by the same amount. So 1 APM at the beginning, I'll multiply that by 5 APM. So the pressure inside the syringe should be 5 APM. So that's what we're doing here. Making a data table here, and basically we have V1 equals to 10 milliliter, okay, and P1 equals to 1 APM. And then we have V2 equals to 2 milliliter, and then we want you to determine P2. So using that table there, P1 V1 equals to P2 V2, then P2 equals to P1 V1 over V2. So in this case here, we have 1 APM, 10 milliliter, and then 2 milliliter here. So this will give you 5 APM. And pay attention to the sig fig there, and I wasn't observing the sig fig when I put it on the board there, and just try to save some time there. So this is the relationship here. Now in this particular case, temperature is not involved. So we can leave the volume in, R is not involved, and we can leave the volume in milliliters. Okay, and so this is in milliliter, and this is in milliliter, and this is in APM. So in the end, the milliliter cancels out. Now we'll give you the pressure, and pressure will be 5 APM. Okay, so that's one type of calculation. Again, you just need to be able to, when you are given a question like this, and try to list out all the quantities and try to identify what's given, what's been asked, and from there you can plug them in the equation and then get the answer here. So the answer would be 5.003 sig fig. That's the pressure in APM. Okay. Another example, how many moles of gas are in the lung of a person with a total lung capacity of 3,000 milliliter at 739 millimeter mercury? Body temperature of 38 degrees. This person may have a little bit elevated temperature there. And then normal body temperature is around 36.5, 37 degrees Celsius there. So this is a gas law equation that and this is a question that we can use gas law equations to determine. So in this case, what's given here is that we're going to use ideal gas law to do this particular equation. So we have volume is given, okay, and that's 3,000 milliliter. And the pressure is 739 millimeter mercury.